Hi everyone, this is Myoungwon from Samsung Electronics. Today, I'm gonna share our observations on the performance of distributed storage system and the implications we got from those. This talk mainly covers the performance challenges of the reliable distributed storage system SAP. Based on that, we have designed and prototyped a new OSD architecture that can achieve more than 3 times speed up for small random byte workload. So what's the problem? As you all already know, SAP's sequential I/O performance is good enough to fully saturate the 10 gigabit network bandwidth, but the random byte performance is rather poor. We only got slightly higher IOPS than the aggregate performance of 3 NVMe SSDs, even though we have total 50 devices. Due to the characteristic of SAP, constancy and correctness are more important things than others, so the performance has always been the main challenging issue in SAP. In order to find the root cause of low random performance, we analyze SAP's write I/O paths in detail. Then our prototype three threading models: baseline, non-completion, and ideal model to figure out where the overhead comes from. First, the figure shows the baseline write I/O path of SAP with the replication factor of 2. When receiving the write request, the primary OSD prepares a replication request to send it the secondary OSD. Then it writes a transaction to the backend store and then forwards a replication request to the replica simultaneously. After the secondary OSD completes the replication request and send X to the primary OSD, the primary OSD reply to the response message to the client. RTC is a run-to-completion model where one thread performs all the tasks required for an IO request. So we don't have context switching already here. In addition, to see the ideal performance when there is only network stack overhead, we revamp SAP's OSD to do nothing to store the object. So only network protocol processing does exist. We call this null test. There are three results showing IOPS, latency, CPU CZ, and write amplification. As explained before, we compare the baseline SAP with two modified versions of SAP, RTC and null. In original case, each node shows CPU usage of 346% while achieving 29 KIOPS in total. The CPU consumption is too high for such a low performance. That is to say, I/O path needs to be highly optimized while reducing CPU consumption. From the experimental results, we have identified problems that exist in SAP and proposed 3 designs to solve the problems. First is decoupled operation processing using NVM. To reduce the write latency, we proposed a design which processes I/O requests differently without losing strong constancy. To do that, our design handles the latency critical job, such as replication processing using operation now, and handles the best effort job in a batchy processing manner. This allows the replicas to give fast response to the client. The next idea is prioritize thread control. We use different threading model depending on the types of thread. There are two thread types: priority thread for latency critical tasks and non-priority thread for the others. The former is responsible for message exchanging and replication processing, while the latter is in charge of storage processing. Third is CPU efficiency object store. We design an in-place update basis object store to minimize the host side WAP and CPU overhead, and to maximize parallelism during storage processing. Since CPU efficient object store runs on low devices, it directly manages metadata, block map, and data areas. So, and there is no cleaning there is no cleaning process such as compaction. Putting them all together, our proposed architecture process are with much less latency and CPU consumption. This is the results. This is the performance results. Our approach can achieve more than 4 times higher IOPS and reduce latency from 4.1 milliseconds to 1.2 milliseconds. When it comes to CPU utilization, almost all cores are utilized in the proposed architecture. But we observe that the original XF OSD does not. It seems like weird, as we say that we reduce the CPU consumption, but this is because proposed design achieve higher IOPS per core than the original case. That's it. Thank you for listening.